Welcome! In calculus, a limit helps us describe what a function is doing near a point, not necessarily at the point. Let's explore this with an example. Consider the function f of x equals x squared minus 1, all divided by x minus 1. Let's see what happens if we try to evaluate the function exactly at x equals 1. We plug in 1 for x. This simplifies to 1 minus 1 in the numerator and 1 minus 1 in the denominator, which is 0 divided by 0. This form, 0 over 0, is called an indeterminate form. It means the function is undefined at x equals 1. So we can't find the value at x equals 1, but with limits, we ask, what value does f of x approach as x gets very close to 1? Let's visualize this. The function simplifies to y equals x plus 1 everywhere except at x equals 1. The open circle at x equals 1 shows the hole in the graph where the function is undefined. Let's pick a point and see what happens as its x value gets closer to 1 from the left side. As x approaches 1, notice that the y value of the point gets closer and closer to 2. Now let's approach from the right side. We'll start our point at x equals 3. As x gets closer to 1 from the right, the y value again gets closer and closer to 2. From both sides, the function approaches a y value of 2. We say the limit as x approaches 1 is 2. Now let's solve this using algebra, which is how you'll handle most limit problems. We start with our limit expression. Since direct substitution failed, we must simplify. The numerator, x squared minus 1, is a difference of squares. It factors into the quantity x minus 1 times the quantity x plus 1. Here is the key idea. In a limit, x gets very close to 1, but it is never actually equal to 1. Because x is not 1, the term x minus 1 is not 0. This means we are allowed to divide the top and bottom by it. After canceling, we are left with a much simpler limit expression. This new expression is simple and defined at x equals 1, so now we can use direct substitution. We substitute 1 for x, which gives us 1 plus 1. This gives us our final answer of 2. The algebraic result matches our visual exploration.